All right, good morning. Hope everybody got their 10 o'clock coffee. Because I find this precursor kind of thing to require a little caffeine to think about clearly. So the focus of what I'm going to talk about is trying to untangle some of these ENSO precursors. And this is work that I've been doing in collaboration with Mike Alexander. So this slide is to kind of illustrate that we have a large number of precursors that have been proposed, and this is nowhere near all of them. This is just all of the ones I could fit on a slide. And the idea is to give you the sense that we have all of these, and we kind of have some idea how each of them may be able to impact ENSO to trigger an El Nino or La Nina, usually through some sort of stochastic processes, like for example, we know westerly wind bursts are important to the development of El Nino, but not all westerly wind bursts lead to an El Nino event. We also know that a lot of these are probably not independent. For example, the Nino-Southern Oscillation is thought to impact and create westerly wind bursts. So of course that is not an independent set of processes impacting ENSO. Some of these processes come from the tropics, some from the extratropics, and the ones I want to focus on today come from the extratropics. It's the MPO seasonal footprinting mechanism and the Pacific meridional mode. And I'm going to focus on the northern hemisphere meridional mode, but there's also been found a southern hemisphere counterpart that can affect ENSO in the same way. So to give an overview of the seasonal footprinting mechanism, it starts with the North Pacific Oscillation in the winter. So that's the sea level pressure dipole that you see here. This is the second leading mode of sea level pressure in the North Pacific, with the first being the Aleutian low. And so you get this dipole, and on the southern lobe of this dipole, you get anomalous winds that oppose the trades and reduce the heat flux out of the ocean. And that leads to a warming of SSTs here in the subtropical Pacific. And this is the so-called footprint of the seasonal footprinting mechanism. And this footprint actually persists into the spring, and then on the southern edge of that, through thermodynamic surface feedback processes, we can get anomalous winds as well, which are now close enough to the equator that they can induce a downwelling Kelvin wave and lead to an ENSO event. So in the case of the signs in this direction, we lead to El Nino, but you can reverse the signs and lead to La Nina. And we also have the Pacific meridional mode, and these two have been talked about in the literature kind of interchangeably. So the real question here is whether these two are the same processes. And so what you see here, this is the meridional mode from Chang and Weimont, and they define this based on a maximum covariance analysis between SST and winds in the subtropical and tropical Pacific. And you see that you get a similar pattern of SSTs in that you get warming here in the subtropics. And this is Hawaii here, so just to give you a reference since I left the longitudes off. So you get warming near Hawaii, you get winds associated with that, and then you get opposite signed SSTs in the eastern Pacific. And this has been suggested as being able to impact ENSO in kind of the same way with similar processes as the seasonal footprinting mechanism. So with some similarities in the patterns and in the processes that impact ENSO, the real question is, are these the same? Are they basically the same mechanism? Are they different? Are they part of the same larger mechanism? If you look at indices from these two, you find that they're certainly not independent. They're correlated at about 0.4. So what I'm going to do is show you some work that I've done to try to separate these two or try to understand if they're the same or different. And so first I'm going to define an index for each one. For the seasonal footprinting mechanism, I'm going to use the NPO. That's the second EOF of winter sea level pressure in the North Pacific. So this is the characteristic dipole. And I'm just going to use the PC time series associated with this pattern to represent the SFM. And then for the meridional mode, Chang and Weimont defined it with a maximum covariance analysis between the SSTs and the winds, so you get two indices. And I really want just one to look at and compare with the SFM. So what I've done is to define the second EOF of SST in the subtropical and tropical Pacific. You get basically the same pattern that Chang and Weimont got, and you get a very similar time series. So I'll use the time series associated with this pattern to represent the meridional mode. So to look at the evolution of these two different precursors to ENSO, I've regressed sea surface temperature and sea level pressure onto each of those indices. So the left is the NPO SFM, the right is the meridional mode, and these are seasonal lagged regressions, so this is time goes down. You have December, January, February prior to El Nino, and the JF with a mature El Nino. And the things I want to point out on this slide are that there are very different evolutions between the SFM and the meridional mode. So if you look at the winter prior to El Nino in both of them, what you see is that for the NPO SFM, you don't have warm SST anomalies in the subtropics yet. You certainly don't have any in the tropics. Whereas with the meridional mode, you see that you already have these warm SSTs. They reach all the way down and are able to actually impact the equator. As you follow the SFM, you see that you develop the warm SST anomalies in the spring, and that they, over the course of the year, evolve into an El Nino event. And they evolve from the Eastern Pacific, which looks like a canonical El Nino. If you look at the meridional mode, this pattern is actually very persistent through the year, and it actually starts in the central, the warming along the equator you have in the Central Pacific, and that it then expands eastward with the maximum SSTs being located more in the Central Pacific. So again, the evolutions are different. You have a persistent pattern, an evolving pattern, and I also want to point out that you see it's not surprising we've kind of thought of these as similar or the same thing, because in the spring, if you look at their patterns, they're quite similar here. You see they're actually correlated about 0.7. So there's some evidence. They're certainly not independent, and it's not surprising we've thought of them as kind of the same thing. And to quickly look at the lagged regression at the subsurface, you see you see that the I'll just point out the spring since I'm running out of time, but you actually see the pattern evolves to the east in the NPO SFM, and you see that their spring subsurface manifestations are quite different. And then finally, I just want to point out that we've been trying to look at how these processes evolve, these mechanisms evolve to impact the equator. And we start here with the idea that the latent heat flux on the southern lobe of that low pressure leads to warming for the NPO SFM, and you see that here. You also see the wind stress curl leads to some ability to transport water onto the equator and some charging. And you see that represented in the sea surface height, where you get increased sea surface heights, a deeper thermocline, sort of all the way across the equator. And that kind of leads to the idea that maybe the NPO SFM is more related to a recharge-discharge oscillator idea of ENSO, whereas the meridional mode, I'll just point out that you see strong zonal wind stress anomalies on the equator that sort of hold the warming in the Central Pacific and then allow eventually for it to propagate east. So it seems the meridional mode is associated more with local wind-driven processes in the Central Pacific. So to conclude, I just want to highlight, it looks like these are different mechanisms enforced by different atmospheric circulations with different evolutions at the surface and subsurface. In the meridional mode, we have local wind stress anomalies in the Central Pacific that seem to force a more Central Pacific ENSO. And in the NPO SFM, we have more basin-wide transport consistent with a recharge-discharge oscillator idea that leads to Eastern Pacific ENSO. And we've done some preliminary work by looking at some models, and we find that many models don't actually capture the meridional mode to ENSO connection, and this may be a reason why models are struggling to capture Central Pacific ENSO events.
Any questions from the floor?
So in defining the NPO as a sea level pressure pattern and a specific meridional mode using sea surface temperature, you're using, say, a forcing of a pattern versus a pattern that already exists. And I wonder if there's a way of disentangling whether or not that disconnect really implies that those two are different.
Yeah, that's a good question. I had thought by doing it that way, I actually thought they were the same thing, and I had thought by doing it that way, I would recover the same thing by, sort of backtracking and recovering the same thing for each. And it didn't quite turn out that way. But I'm not quite sure of the best way to go about how to really clearly separate them.
How strong are these precursors if you did a simple correlation between the precursor and, say, Nino 3.4? How strong would it be over what lag be?
Yeah, so it depends on how you define the precursors, but in the way that I've done it here, the MPO is actually not nearly as strong as the meridional mode because, again, I'm using a sea level pressure to define the MPO, and so it's much noisier, whereas the SST-based precursor is much more clearly connected to ENSO and less noisy. But the correlations are on the order of about 0.4-ish